Mathematics in medieval Europe. Combinatorics, the mathematics of kinematics. Velocity, the Merton theorem. The Oresme's fundamental theorem of calculus. Combinatorics. It is the ancient branch of mathematics. It is defined a finite mathematical system then solve problems related to the selection or arrangement of a number. In medieval Europe, there was also interest in such questions primarily in the Jewish community. The earliest Jewish source on this topic seems to be mystical work Sefer Yetzirah, the Book of Creation. Combinatorics of the Sefer Yetzirah. It describes that the universe was created by God of Israel through the 32 wonders of God, 10 numbers of Sephirot, and 22 letters Hebrew alphabet. The Book of Creation was written sometimes before the 18th century and perhaps as early as the 2nd century. It is the unknown author calculated that the various way in which the 22 letters of the Hebrew alphabet can be arranged. He was interested in this calculation because the Jewish mystics believed that God had created the world and everything in it by naming these things. God drew them, combined them, weighed them, interchanged them, and through them produced the whole creation and everything that is destined to be created. Sefer Yetzirah. The author understood that the number of possible arrangement of n letter was n factorial. Shabtai Donolo, an Italian rabbi, derived this factorial rule. The first letter of the two-letter word can be interchanged twice, and for each initial letter of the three-letter word, the other letters can be interchanged to form two-letter words. For each of the 3 times, and all the arrangement, there are 3-letter words correspond to each one of the 4 letters that can be placed first in the 4-letter word. A 3-letter word can be formed in 6 ways, and so for every initial letter of the 4-letter word, there are 6 ways, altogether making 24 words, and so on. Abraham Eben Ezra. Although the author of Sefer Yetzirah briefly mentioned how to calculate the number of combination of letters taken 2 at a time, a more detailed study of combination was carried out by Abraham Eben Ezra, a Spanish Jewish philosopher, astrologer, and biblical commentator. It was in astrological texts that Eben Ezra discussed the number of possible conjunction of the 7 planets, including the sun and the moon. It was believed that this conjunction would have a powerful influence on human life. Eben Ezra thus calculated combination of 7 taken k at a time for each integer, k from 2 to 7, and noted that the total was 120. He began with the simplest case that the number of binary conjunction was 21. This number was equal to the sum of the integers from 1 up to 6 and could be calculated by Eben Ezra's rule for some of the integers from 1 up to the particular number. Multiply that number by its half and by the half of unity. In modern terms, we can write this as combination of n taken 2 at a time is equals to n minus 1 summation I is equals to 1. I is equals to n minus 1 times n minus 1 over 2 plus n minus 1 times 1 over 2 is equals to n times n minus 1 over 2. To calculate ternary combination, Eben Ezra explained, we begin by putting Saturn with Jupiter and with them one of the others. The number of the other is 5. Multiply by 5 by its half and by the half of unity. The result is 15. And these are the conjunction of Jupiter. Namely, there are 5 ternary combinations involving Jupiter and Saturn, for involving Jupiter and Mars but not Saturn, and so on. Hence, there are combination of 6 taken 2 at a time is equals to 15 times equals to 5 times 5 over 2 plus 5 times 1 over 2. Ternary conjunction involving Jupiter. Similarly, to find the ternary conjunction involving Saturn but not Jupiter, Eben Ezra needed to calculate the number of choices of 2 planets from the remaining 5. Combination of 5 taken 2 at a time is equals to 10. He then found the ternary conjunction involving Mars, but neither Jupiter nor Saturn. And finally, concluded with the result, combination of 7 taken 3 at a time is equals to combination of 6 taken 2 at a time plus combination of 5 taken 2 at a time plus combination of 4 taken 2 at a time plus 3 combination of 3 taken 2 at a time plus combination of 2 taken 2 at a time is equals to 15 plus 10 plus 6 plus 3 plus 1 is equals to 35. Evan Ezra next calculated the quaternary conjunction by analogous method. The conjunction involving the Jupiter requires choosing 3 planets from the remaining 6. Those with Saturn but not Jupiter require choosing 3 from 5. So finally, combination 7 taken 4 at a time is equals to combination of 6 taken 3 at a time plus combination of 5 taken 3 at a time plus combination of 4 taken 3 at a time plus combination of 3 taken 3 at a time is equals to 20 plus 10 plus 4 plus 5 is equals to 35. Evan Ezra then stated the result of the conjunction involving 5, 6, and 7 planets. Essentially, he had given an argument for the case n is equals to 7, easily generalizable to the general combinatorial rule. C or combination of n taken k at a time is equals to n minus 1 summation I is equals to k minus 1 combination of I taken k at a time minus 1. The mathematics of kinematics. The kinematics is subfield of physics developed in classical mechanics that describe the motion of points, bodies, objects, and system of bodies, groups of objects without considering the forces that cause them to move. Kinematics as a field of study is often referred to as geometry of motion and is occasionally seen as the branch of mathematics. A kinematics problem begins by describing the geometry of the system and declaring the initial condition of any known values of position, velocity, and or acceleration of points within the system. Then using arguments from the geometry, the position, velocity, and acceleration of any unknown parts of the system can be determined. The velocity of a particle is a vector quantity that describes the magnitude as well as the direction of motion of the particle. More mathematically, the rate of change of the position vector of the point with respect to the time is the velocity of the point. Consider the ratio formed by dividing the difference of two positions of the particle by the time interval. This ratio is called the average velocity over the time interval and is defined as v avg is equals to delta r over delta t, where delta r is the change in the position vector during the time interval of delta t, in the limit that the time interval of delta t approaches 0. The average velocity approaches the instantaneous velocity defined as the time derivation of the position vector, where the dots denotes the derivation with respect to the time. Thus, the particle velocity is the time rate of the change of its position. Furthermore, this velocity is tangent to the particle's trajectory and every position along its path. Note that in non-rotating frame of reference, the derivatives of coordinate directions are not considered as their directions and magnitudes are constant. The speed of an object is the magnitude of its velocity. It is a scalar quantity, where s is the arc length measured along that trajectory of the particle. This arc length must always increase as the particle moves. Hence, ds over dt is non-negative, which implies that speed is also non-negative. The velocity vector can change in magnitude and in direction or both at once. Hence, the acceleration accounts of both the rate of the change of the magnitude of the velocity vector that the rate of change direction of the vector. Velocity vector can change in magnitude and in direction or both at once. Hence, the acceleration accounts for both the rate of the change of the magnitude of the velocity vector and the rate of the change of the direction of the vector. The same reasoning used with velocity can apply to the velocity to define acceleration. The acceleration of the particle is the vector defined by the rate of the change of the velocity vector. The average acceleration of the particle over the time interval is defined as the ratio. A is equals to delta v over delta t, where delta v is the difference in the velocity vector and delta t is the time interval. The acceleration of the particle is limit of the average acceleration as the time interval approaches 0, which is the time derivative. Thus, acceleration is the first derivative of the velocity vector and second derivative of the position. Thus, acceleration is the first derivative of the velocity vector and the second derivative of position vector of that particle. Note that in non-rotating frame of reference, the derivative of the coordinate direction are not considered as their direction and magnitudes are constant. The ancient Greeks applied analysis only to the static problems, either to the pure geometric or to the forces in equilibrium. Problems involving motion were not well understood, perhaps because of the philosophical doubts exemplified by Zeno's paradox or because of Aristotle's erroneous theory that motion requires the continuous application of force. Analysis began its long and fruitful association with the dynamics in the Middle Ages, when mathematicians in England and France studied motion under constant acceleration. They correctly concluded that for a body under acceleration over a given time interval, total displacement is equal to time times velocity at the middle instant. This result was discovered by the mathematician at Merton College, Oxford, in the 1330s, and for the reason it is sometimes called the Merton acceleration theorem. A very simple graphical proof was given about 1361 by the French bishop and Aristotelian scholar Nicolas Oresme, or also known Nicole Oresme. He observed that the graph of velocity versus time is a straight line for constant acceleration, and that the total displacement of an object is represented by the area under the line. This area equal the width, length of the time interval times the height or the velocity at the middle of the interval. Nicolas Oresme or Nicole Oresme was a French Roman Catholic bishop, scholastic philosopher, economist, and mathematician whose work provides some basis for the development of modern mathematics and science and of French prose, particularly its scientific vocabulary. Oresme is also considered one of the most eminent scholastic philosophers, famous for his independent thinking and his critique of several Aristotelian tenets. He rejected Aristotelian's definitions of a body's place as the inner boundary of the surrounding medium in favor of the definition of place as the space occupied by the body. Similarly, he rejected Aristotle's definition of time as the measure of motion, arguing instead for the definition of time as the successive duration of things independent of motion. Oresme was a determined opponent of astrology, which he attacked on religious and scientific grounds. In De Proportionibus Proportionum, on ratios of ratios, Oresme first examined raising rational numbers to rational powers before extending his work to include irrational powers. The result of both operations he termed irrational ratios. Although he considered the first type commensurable with rational numbers and the later not, his motivation for this study was a suggestion of the theologian mathematician Thomas Brandwarden that the relationship between forces, resistance, and velocities is exponential. Oresme then asserted that the ratio of any two celestial motion is probably incommensurable. This includes precise prediction of successive repeating conjunction, oppositions, and other astronomical aspects, and he subsequently claimed in Ad Pauca Respecientes, its name derived from the opening sentence concerning some matters. that astrology was thereby refuted. As with astrology, he fought against the widespread belief in the occult and marvelous phenomenon by explaining them in terms of natural causes in Livre de Divinations, Book of Divinations. Oresme's main contribution to the mathematics are contained in his Tractatus de configurationibus, qualitatum et motuum, Treatise on configuration of qualities and motion. In this work, Oresme received the idea of using rectangular coordinates, latitudo and longitudo, and the resulting geometric figures to distinguish between uniform and non-uniform distribution of various quantities, even extending his definition to include the three-dimensional figures. The fundamental theorem of calculus, differential and integrals. The method of Fermat and Descartes is part of what is known as differential calculus, and indeed it deserved the name calculus, being a systematic and general method for calculating tangents. At the same time, mathematicians were trying to calculate other properties of curved figures such as their length, area, and volume. These calculations are part of what is known of integrals calculus. A general method for integral problems was not immediately apparent in the 17th century, although algebraic techniques worked well in certain cases, often in combination with geometric arguments. In particular, contemporaries of Fermat and Descartes struggled to understand the properties of the cyclone, a curve not studied by the ancient. The cyclone is traced by the point on the circumference of the circle as it rolls along the straight line.